Hello, today I am going to start a new module which will deal with compression member. A structural member when subjected to axial force only, then such type of structural member is called compression member. Now, different type of structures compression members are termed as different way. Like in case of RCC building, such type of compression member is called column. Column is or this in case of RCC building, this compression member or column is basically a vertical member which carries the load from beam or from the floor and transferring from upper floor to lower floor. Similarly, in case of steel building, this type of compression member is called stanchion. Again, the compressive member in a roof truss or bracing is called strut. Similarly, the principal compression in a crane is called boom. So, what we could see that the same compression member are termed different in different name for different cases. Now, when we will go for calculation of strength of the compression member or when we will go to design a compression member, then we have to see that what are the type of failure come into picture for a compression member. Depending on the type of failure, we have to find out what are the strength can be carried by that type of member, that particular member. So, in case of compression member, there are different type of failures occurs. Out of them, one is called squashing. This squashing is basically happens when the length of the compression member is quite less compared to its transverse direction, cross sectional area dimension. Like say for example, if a member is like this and taking compression load, then in such case of member the crushing will come into picture mainly, and full strength will attain at its yield strength, and therefore, the failure load can be calculated yield strength into the cross sectional area. Failure load will be calculated simply the yield strength into its cross sectional area. So, in such cases we could see that the member fails due to crushing of the material. That is what one type of failure we could observe. Another failure is the local buckling. Local buckling happens due to its cross sectional configuration. In case of steel building, we know that local buckling means the member we use different type of rolled section, steel rolled section. Say for example, we oftenly use the channel section. So, in such case what will happen that due to compression, this web may buckle individually, this flange may buckle individually, or some other part of the member may buckle, which is called local buckling. So, it has to be taken care while calculating the compressive strength of the member. Then another type of failure will be that overall flexural buckling. When the member length along its axis is quite high compared to its cross sectional dimension, then such type of buckling occurs, which is called flexural buckling. Say for example, we have a long column means compared to its lateral dimension. So, in such cases it may buckle in this way. So, before going to fail due to crushing, it may fail due to buckling. So, such type of buckling phenomena has to be taken care while considering the strength of the compression member. Again, if we see the cross section, say for example, this, if the cross section is something like this, then you can see it may buckle about this axis, it may buckle about this axis. So, we have means in which direction it will first buckle? It will buckle about the weaker direction, weaker section. So, in this case it will buckle about this. Then another failure may come due to torsional buckling. Torsional buckling failure occurs due to torsional moment. The member get twisted about the shear center in the longitudinal axis. So, torsional buckling may occur maybe in case of angle section or channel section, depending on the type of load, means acting in a particular place, means load will be compressive, but where it is acting, whether it is acting in the member axis or it is CG, depending on that the torsion will come into picture, torsional moment, and because of that torsional buckling may occur. Another scope of buckling is called flexural torsional buckling. This is nothing but the buckling which occurs when the member bends and twists simultaneously. That means, member will bend, again it will twist, means it may twist like this, maybe like this, it may twist. Such type of failure happens generally in case of unsymmetrical cross section. So, unsymmetrical cross section means, say for example, channel section, it is symmetric about this direction, but it is unsymmetric about this direction. So, in which direction it is unsymmetrical, depending on that we have to consider whether it is unsymmetrical cross section or symmetrical cross section, and accordingly the torsional buckling will come into picture. Now, while calculating the compressive strength of a compression member, we have to find out, means what type of effect is coming on a particular compressive member. It depends, this effect depends in length of the compressive member. Like one is called short compressive member. Short compressive member means what I told earlier, that suppose a member is length is quite short compared to its width and thickness, means if its width and thickness is substantial with respect to moment, that means the L by R ratio is quite low. In that case, the failure stress will be equal to the yield stress, and there will be no buckling. Buckling will not happen in this case. So, here it will fail due to yielding of the material. So, this is happens when short compression members are means when the members are short compression. And another type of member which is called long compression member. In this case, stress will occur due to buckling. That means, in this case means maybe its height is like this or length is like this, but its cross section is quite less, right. So, in this case buckling may happen before yielding of the stress. That is why we need to consider whether it is long compression member or not, and accordingly we have to find out what type of means stress is developing due to buckling or due to yielding. Accordingly, the compressive strength of the member will be considered. Another case is intermediate compression member. In case of intermediate compression member, failure occurs due to the combined effect of crushing and buckling. Intermediate compression in practice, most of the members are considered as intermediate compression member, because in this case the member will undergo both the stress. One is due to crushing, due to compression of the member, it will shorten its length and it will crush, and another is due to its length, it will buckle something like this. So, buckling stress will come into picture as well as crushing stress will come into picture. So, both the effect we have to consider, and we have to find out the failure strength of the member, and most of the cases the compression member acts as intermediate compression member, where both the effects will have to be taken care. Now, for finding out the compressive strength of a member, as we see that one is the crushing value we have to find out, that means yield strength. We have to find out the yield strength of a particular material, and accordingly the strength of the compression member can be calculated. Another is it may buckle. So, due to buckling, what will be the buckling force and what will be the stress, that we have to find out, and for that Euler has considered a ideal column and has find out a critical load for buckling. That critical load which has been obtained due to buckling are derived on the basis of these few assumptions. That is, one is the material is homogeneous and isotropic. That means, the material along the throughout its length will be homogeneous and isotropic. There will be no change of material properties. Then material is perfectly elastic. That means, up to elastic limit this buckling theory will be considered. This will be true for up to elastic limit. Then no imperfection, that means, member will be perfectly straight at its initial state and there will be no flaw of the geometry and material across the member. Then there should not be any eccentricity of loading. That means, the in case of Euler theory, the derivation has been made considering the concentric loading. That means, there will be no eccentric loading acting on the member. And another is column ends are hinged. While developing this theory, it has been considered that column ends are hinged and column has no flaw. With these assumptions, Euler has suggested a buckling theory which is given here. That is, if a load, compressive load is acting on this member, along this member, then and if there is a compressive force P, and if buckle happens like this, then at a distance of x the displacement will be y and the governing differential equation will be d2y dx square plus p CR EI into y is equal to 0. P CR is nothing but the critical load which will come, means which will be derived, right. That P CR is the critical load which can be found from this governing differential equation, and from the governing differential equation the lowest value can be found as like this, that P CR as pi square E I by L square, where L is the effective length. Effective length means I will come later, because length between the end of the column will be the total length. This is total length. Now, effective length will nothing but the length where the two moment of contraflexures are occurring, distance between that two. Like in case of if it is fixed, it will buckle like this. So, effective length will be this is L, right. So, P CR will be pi square E I by L square, where L is the effective length and E I is the modulus of rigidity. Therefore, the sigma CR, the critical stress, can be found as P CR by A, where A is the cross sectional area of the column, and if we use the value of P CR here, then it will be pi square E I by A L square. So, further if I write I as I by A as, we can write I by A as R square. So, sigma CR value will be pi square E R square by L square, and then again if we derive, it will be pi square E by L by R whole square, which is pi square E by lambda square. Lambda means lambda is equal to L by R. Lambda is nothing but the slenderness ratio. R is the radius of gyration, and radius of gyration means minimum radius of gyration. In two direction radius of gyration will occur, and about minimum radius of gyration it will fail fast. That is why the minimum radius of gyration will be considered. So, sigma CR, the critical stress, can be found as like this, pi square E by lambda square, where lambda is equal to L by R. So, we can see that critical stress is inversely proportional to the slenderness ratio or inversely proportional to its length, right. So, critical stress will be increasing if the value of lambda is less, or reversely I can say the critical stress will be less if the slenderness ratio is more. So, the critical stress using Euler buckling theory can be found from this, which will be used for deriving the compressive strength of the column. Now, for an ideal strap, the strength curve of a column can be derived if the strut is actually loaded and initially straight with pin ended, then this can be derived in this way, where x axis will be the slenderness ratio, that is L by R, and y axis will be the compressive strength of the material. So, here we see the path is varying from A to C and then C to B, right. So, column fails when the compressive stress is greater than or equal to the values defined by ACB. That means, this is the path defined, and if column stress is coming somewhere here or here, that means it is failed. So, if the column stress is going to be greater than the stress defined by this path ACB, then I can say that column is going to fail, and this AC is basically failure by yielding. And if we consider low slenderness ratio, then failure may happen due to yielding, and failure may happen due to buckling if for high slenderness ratio, that is due to this. And you see failure will happen due to buckling if lambda is greater than lambda c. If lambda, this is lambda, if lambda is greater than lambda c, then it will come due to means the failure will come due to buckling, right. So, this is basically plastic yield, and this is defined by F c is equal to F y, and this is defined by pi square E by lambda square, that is elastic buckling stress. And if we consider that F c is equal to sigma CR is equal to F y, that means the yield stress, if we consider yield stress as sigma CR critical stress, then from that I can find out lambda c as is equal to E by pi into root over E by F y is equal to 88.85. It is a constant. This is constant for a particular, this 88.85 will be for a particular value of E and F y, where E is equal to 2 into 10 to the 5 and F y is equal to 250. For this value, lambda c value could be found as like this. However, for other still this lambda c value will be different. So, what we could see from this curve, that if the lambda value, slenderness ratio value become more than 88.85, then it will fail by elastic buckling, and if it is less than that, it will fail by plastic yield. Due to plastic yield, it will fail. Now, the same can be written in a non-dimensional form as well, which is shown here, where in y axis it is a F c by F y, and it will be 1 because where F c and F y will be 1 here, means will be equal here, and lambda c will be 1 here, means lambda bar will be 1, where lambda c by lambda will be 1, and in this direction, in x direction, lambda bar, which is square root of F y by sigma CR, has been plotted. So, this curve will be elastic buckling, and this will be plastic yield. So, this is how the strength curve for an ideal strut can be developed by the Euler's theory, but this cannot be applied for a practical case, because in case of practicality there are certain parameters which will affect on the compressive strength of the member. Therefore, we will consider a separate, means a different formula. However, this formula is based on this elastic, means Euler buckling theory, as well as some other factors also has been included. So, that will come in next. Now, if we see the factors which are going to affect on the strength of compression member, we can see that first is the material property of the member. So, the compressive strength, if we see sigma FCD, if I say FCD compressive strength, FCD, the design compressive strength FCD, if we say, it depends on Fy, that means yield strength of the member, that means it depends on the material property of the member. This is one. Another factor is the length of the member, because we have seen the Euler critical load is inversely proportional to the radius of gyration and thereby the length. So, if length is more, then definitely the compressive strength will be means compressive load carrying capacity will be less. So, it affects on the member as well. So, this has to be taken consideration. Then that means this is due to overall buckling and this is due to crushing, and this cross sectional configuration. Cross sectional configuration means in case of RCC member there is no problem, because there will be no local buckling, because generally in case of RCC member either rectangular section, square section or circular section we use in general. But in case of steel member we use different type of built up section, say for example built up section or rolled section. This is a built up section we are using, channel facing each other, channel face to face, or we can make some I section also, say I section also can be used. So, here what we can see that due to cross sectional configuration local buckling of the flange or web may happen. So, that has to be taken into consideration. Another thing is the support condition. Support condition why we should take, because in case of hinge support, the length will be, the effective length will be simply L is equal to L. But if we see, if this is a fixed support, then its buckling curve will be like this, and we know that the L will be basically L by 2, right. So, effective length is going to reduce. So, as length of the member affects on the compressive strength in the member, therefore, support conditions also affects on that. Next is the imperfection. Now, imperfection means that material may not be isotropic truly and homogeneous, then geometric variation of the column may be there, that means cross sectional cross section throughout the length of the column may not be same exactly, then eccentricity it may not have exactly eccentricity. So, these imperfections also affect on the strength on the member. Therefore, that has to be also taken care in our design. Another is the residual stress. If residual stresses are there in the member, then the compressive strength is going to be different. So, that aspects also has to be keep in mind. Now, coming to the cross section of the member, if we see that in case of column or compression member, different type of steel rolled sections which are available in the market can be used for compressive member. Like single angle section, we can use single angle section. However, while using single angle section, if the member means if the load come into means act on a leg of a member, then the eccentricity will develop, and therefore, the torsional buckling will come into picture. So, we have to take care the strength of the member accordingly. Similarly, for double angle also we can use in this way, or T sections can be used for compressive member. Most popularly used compressive member is channel section. Channel section we oftenly use for compressive member. Hollow circular section also we use, rectangular hollow sections also are used. So, these are few steel rolled section which are commonly used for compressive member. Then some built up sections are also used, like channel face to face. This is one type of built up section we use. Then channel back to back, this also use. So, now suppose channel face to face or back to back, if we use say for example this. Now, we cannot use simply like this, because if we see in the elevation, it will be something like this, right. So, unless we tie them, unless we provide some lacing, then it will not act as a monolithic. Therefore, we have to provide certain either some joint means in terms of batten plate or some lacing has to be provided, so that throughout the length it acts as a monolithic member. So, this has to be taken care. And another is built up box section, means with 4 plates one can make built up box section, then plated I section, then built up I section. Like this, some of the commonly used built up compression members are there. Then we will come to the effective length factor. Effective length factor means here we see the LE, as we have written the effective length LE is equal to K into L, where K is the effective length factor. Now, this K depends on the restraint condition of the member. As I have told that in case of say suppose fixed column, it will buckle like this. So, point of contraflexure will be here, another point of contraflexure will be here. Point of contraflexure means where the moment is becoming 0. Now, this distance between two point of contraflexure becoming as effective length LE, right, where capital L is the total length of the member, right. So, what will be the value of K? So, here theoretically we got K value as half, that means LE is equal to L by 2, that means 1 by 2 into L. So, this is half. However, in IS code this is considered as 0.65, because it will not be perfectly fixed and it will not be perfectly 0.5. Theoretically, though we are getting 0.5, we are going to consider as 0.65 with certain conservative factor of safety, right. Similarly, when columns with both ends are pinned, we are considering 1, K value as 1, that means L is equal to L. Again, columns with one end fixed and other end pinned, in this case theoretical value though it is coming 0.7, but in IS codal provision it is 0.8. Again, column with one end fixed and other end free, means like cantilever beam, cantilever column, theoretical value is 2, also we are considering 2, means in IS code also it is considering 2. Columns partially restrained at each end will be 1, however, it is considered as 1.2. Similarly, columns with one end unrestrained and other end rotation partially restrained, it is 2. So, when we are going to consider the effective length of a member, we have to go to table 11 of IS 800/2007, and as per table 11 of IS 2007, we have to find out the effective length of the member. This a snapshot of the code of table 11 of IS 800/2007 has been shown here. Here the effective length factor has been given here. Now, another thing we will discuss here, that is the effective length of column in frame, because in practical cases we have to calculate the effective length in a frame, and it is not a separate member, column member is not separate or compression member is not separate, it is inside the frame. So, what should be the effective length of column in a frame, that has to be, that we have to know, and that is given in annexure D of the IS 800/2007. Annexure D in clause 7.2.2 it is mentioned. So, in annexure D, for non-sway frame the K value are given. That K value is 1 plus 0.145 beta 1 plus beta 2 minus 0.265 beta 1 beta 2 by 2 minus 0.364 beta 1 plus beta 2 minus 0.247 beta 1 beta 2. And in annexure D 1 of IS 800/2007, this formula is given, which will be required to find out the value of K for non-sway frame. That means, that is braced frame, when bracings are there. If a frame is there and non-sway means bracings are there, in such cases the K value can be calculated by this, and this is basically proposed by Wood, which is known as Wood's curve, from which the K value has been derived. And for sway frames, that means the moment resistant frame, that means sway frame means just it is like this, say it is a 2-story frame. So, if we see like this, so this is a sway frame or moment resistance frame. So, in this case k value will be like this, that is 1 minus 0.2 into beta 1 plus beta 2 minus 0.12 beta 1 beta 2 by 1 minus 0.8 beta 1 plus beta 2 plus 0.6 beta 1 beta 2 whole to the power 0.5. So, this is also given in annexure D, from which we can find out the value of k. Here beta 1 and beta 2 can be found from this, that is the stiffness of the member and stiffness of the column and stiffness of the flexural member, which is written here that Kc and Kb are the effective flexural stiffness of column or beam. Kc is for column, beam Kb is for beam, meeting at the joint at the ends of the columns and rigidity connected at the joint. So, this is how we have to find out the stiffness, relative stiffness of the effective stiffness of the beam and column connecting at that point. Then we have to find out beta 1 beta 2, right. So, once we find beta 1 beta 2, we can find the value of k. So, this is how effective length of column in frame, whether it is sway or non sway, based on that we can find out the effective length of column, right. So, this is what in today's lecture I would like to discuss, I wanted to discuss. So, in short, again I am repeating the gist of today's lecture, that in a compression member the compressive strength depends on different factors like length, restraint condition, imperfection, residual stress, then material properties. So, all these consideration has to be done. Also the cross sectional configuration is an important part, which come into picture for considering the strength of the member. So, again the slenderness ratio, which depends on the length, effective length and the radius of gyration. So, as per the slenderness ratio, the compressive strength will vary. We have seen that it is inversely varying with slenderness ratio. So, those are the some parameters which have to be taken care, and then while finding out the slenderness ratio, we need to know the effective length, and effective length for different restraint condition that has been given in the code. So, as per codal provision, we have to find out the effective length of a particular member, and also in case of frame, depending on the basis of sway or non sway, the k value, the effective length factor can be found. So, this is how we can decide the length of the effective length of a column or a compression member, which will in turn will be required for calculating the column strength or compression member strength. In next class, we will find out, we will try to find out the compressive strength of a compression member. Thank you.